Well, good evening, everyone. Today, I'd like to discuss a topic on multi-agent deep deterministic policy gradients. It's a common algorithm that's used in deep reinforcement learning in environments where there's multiple agents that are either cooperating with one another or competing with one another to in different applications. And we'll talk about the MADDPG algorithm itself, and then discuss some of those applications of some of those test environments and how this algorithm fares, compared to traditional DDPG algorithm. So with that introduction, let me pull up the slides. So this is the 13th webinar for the Deep Reinforcement Learning Nano Degree at Udacity, and we've covered quite a few topics up to this point. And this is kind of a more advanced algorithm. It builds on one of the actor-critic algorithms we talked about last week, the week before, deep deterministic policy gradients. So actually, to start with, probably should reference the references. This is a review of a research paper by Ryan Lowe and others, with the title "Multi-Agent Actor-Critic for Mixed Cooperative Competitive Environments." And I have the archive link there. It's an interesting paper. I really would encourage you to pull the paper up and take a look at it on your own. But this is just sort of introduction to that paper, and there's certainly more detail in the paper itself that I won't cover this evening, but I'll try to touch on the main topics. So the objectives today primarily really describe the problems that traditional algorithms might have when there's multiple agents either cooperating or competing with one another in a single environment. And then introduced this multi-agent DDPG algorithm that is the main topic of the discussion this evening. And then at the end, kind of compare the performance of this new MADDPG algorithm to the traditional DDPG algorithm, and see how this extension actually does a better job in these types of environments. So to begin with, there's a couple of problems with multi-agent environments. So let's talk about those. The first one really is a situation that complicates learning, and it's when environments are non-stationary. So typically in the environments we've talked about in the past, the environment is pretty much the same from episode to episode, and the agent can run multiple episodes and kind of see the same things in different states. He would see the same observations and be able to fine-tune actions to take in those particular states. But when you throw additional agents into the picture that are either competing with or cooperating even with the agent that's trying to learn the environment, that makes the environment change as these other agents take their actions in the environment. It really complicates the first agent's ability to really understand the environment and know what action would be best in a particular situation. And the actions of the other agents might change what action is appropriate, even with the same observations. The second problem is that as you have more and more agents, the gradients increase in variance, and that additional variance really complicates the policy gradient kind of techniques, and it becomes more difficult to learn, and learning is slower, and maybe becomes unstable. So now let's talk about this MADDPG algorithm and see how it addresses some of those concerns, and how it works to solve some of these problems and improve learning in an agent's learning of the environment. So it's really a real simple concept, and it's based on a framework where the agent has two key things. One is centralized training, and the other is decentralized execution. So what do we mean by those two things? Well, centralized training means that the agent that's learning about the environment can actually share experience from all the other agents that are interacting in the environment. And all those different agents' experiences can be put into a single shared experience replay buffer. And then the first agent has access to all that experience and can use that to, this kind of helps with the non-stationarity idea here. By having knowledge of everything that's going on with all the other agents, it kind of helps the first agent understand the environment better and be able to learn better actions to take in different situations. You might think that would work in execution also, but the problem there is that if you actually enforce that in execution, it means that every agent basically has to be omniscient and know about every other action taking place in all the other agents, and that kind of could complicate execution environments. So the goal is that even though you might take advantage of all that extra information during training, you do not want to have to rely on all that data during execution, and the agent ought to be able to, the trained agent ought to be able to take what it sees in the environment and, based on its training, take appropriate actions in that environment. So, so again, centralized training, but then decentralized execution. So how's this accomplished? Really, the author started with a classic algorithm for actor-critic type of environment, of training environments, and that's the DDPG algorithm, one that you should be very familiar with. The final two projects in this course. It's not required, but most students end up using DDPG as the algorithm that's implemented to solve those two environments. And in fact, in the final project, MADDPG, the multi-agent version of that, is the one that most students actually try and find success using. So it's useful to understand this algorithm, and it's a very simple extension to DDPG. The simple answer is that the critic part of the algorithm is augmented to take information about the policies of other agents. This can be, directly the policies can be shared, or the experience replay buffer can be shared, or the critic might be programmed just to infer those policies by looking at that shared experience replay buffer. But the actor only has access to local information. So the two key parts of the DDPG algorithm are two separate parts to begin with, and one part, the critic, is changed. The actor kind of really stays the same as it was implemented in DDPG, with no real change there. This is a diagram from the paper, and it just sort of illustrates those concepts. You can see that during training, which is the outer green area, there's the actors in the red area. I'll start with that, I guess. The actors are developing and learning a policy based on an offset of observations. They're choosing actions, and during training, that information is fed into the critic network to come up with the Q value, to estimate a Q value. But also here you can see that there's multiple actors, and during training, all that information from all the actors is fed into each and every one of the critics in order to be able to better understand how these interacting agents impact the environment, and be able to get a better estimate of the value of each action that's taken in those individual states. But then during execution, that green area is sort of ignored, and only the actor using local information is used to observe the state space, and based on the policy that's been learned, choose the appropriate actions based just on those observations. So pretty simple extension really to the DDPG algorithm. So let's talk about some test environments. A good part of the paper talks about a set of half a dozen or so different environments that they exposed this algorithm to, and then compared to the baseline DDPG algorithm. And these are just some of those environments. They're kind of interesting in their own right. From a individual project kind of perspective, any one of these could have been a project to experiment with deep reinforcement learning. So the first of these was cooperative communication, and in this environment, there's a couple different agents. One is a speaker, one's a listener, and the speaker basically tells the listener which of these other objects or landmarks that are in the environment that the listener should try to navigate towards. And so this is kind of a cooperative environment. A second cooperative environment is called cooperative navigation. And in this one, there's just a set of cooperating agents and a set of landmarks. And the goal is for all of the agents working together to cover all of the landmarks. And so, if they all happen to go to the same landmark, there'll be a lot uncovered. They have to kind of cooperate with one another to sort of decide who's going to cover which one, and each move throughout the environment to provide that coverage over the landmarks. Then a competitive environment is a keep away. In this one, it's sort of a combination actually of competition and cooperation. The cooperative agents, there's a set of them, they all know a target landmark and they all try to navigate towards it. But the adversaries, which are also a number of those agents, they try to get in the way and prevent the cooperating agents from reaching their goals. So each one of them have a different goal in they're trying to optimize for, and they all are all learning these things at the same time. Another environment, physical deception, is sort of again a combination of cooperation and competition. There's a set of cooperative agents, and they know a target landmark, and they attempt to navigate towards it. And at the same time, there's a lone adversary. And the difference is that while the cooperative agents know which landmark is the target, the adversaries don't, or the adversary doesn't. And so it's sort of it's called physical deception, because the idea is that the cooperating agents, they somehow have to try to deceive the adversary from inferring which target is the landmark that's the target one that's supposed to be navigated towards. And while they're trying to deceive that adversary, at the same time they're also navigating towards that target. So kind of an interesting environment there. Another truly competitive environment is predator to prey. In this one, there's actually a set of cooperating agents. They are relatively slow in moving, and they try to chase a fast adversary. There's a set of landmarks in the environment that impede motion, and the agents that are these slower agents that are trying to track down this adversary, they're given information about the locations and velocities of each other and of the target prey, as well as the location of the landmarks. And they since the adversary can move quicker, he has an advantage, but there's only one of him, so the cooperating agents can work together to try to pin him down and actually be able to have one or more of the cooperating agents cover the fast agent, and that gives them a point in the competition. That's a very traditional environment. You see that not in just deep reinforcement learning, but in a lot of different environments for a lot of different methods of trying to solve that particular problem. And the last one that they talk about is covert communications. This is they use Alice and Bob as an example. That's the common terms used for encrypted communication channels. So Alice wants to communicate with Bob. They have to come up with a method of encrypting their communications so that they can understand what's going on, but an adversary that's trying to listen in would be confused and not be able to understand their message. And so they work together to try to come up with that communication channel, while the adversaries at the same time trying to learn that same information and eavesdrop on their communications. So I might mention, I was kind of surprised at how simple the actor network was that they used in all these environments. These are, to me, I thought, pretty complicated environments, and yet even so, the actor network is a pretty simple neural network. It's a two-layer network, only 64 neurons in each one, simple ReLU activation, and then a softmax kind of action selection on the output layer. So pretty simple neural network, and I think you might have found in the first project, a simple network of 32 or 64 neurons, a couple layers, was actually better at solving that navigation environment than a more complicated network might be. So it's kind of sometimes counterintuitive of how complex these networks have to be. The typical DDPG networks often have 300 to 400 neurons in a layer, so this is a much simpler version of that network. So let's talk about some test results here. I won't go through all the test results. There's quite a few different charts that they present and different comparisons that the authors make. But let's just talk about this one. It's kind of interesting. These are 4 of the more complicated environments: the predator to prey, physical deception, and covert communications. And what this chart kind of shows is they trained agents both with MA multi-agent DDPG and standard DDPG, and then kind of compared the performance of the agents against one another. So when both the agents were the multi-agent DDPG, both the cooperating and the competitive side of that equation, that's the first set of bars there, and you can see that in some of the environments, the agent did quite well compared to the adversary, even though they were both using the same algorithm. For example, physical deception with n equal 2 and n equal 4 both did pretty well, as well as covert communication, surprisingly. I think that seemed to be one of the more difficult ones, and yet it did pretty well. Predator prey, not quite as well, maybe 0.2 agent score, and so it didn't quite do as well in that version when they were both multi-agent. The more interesting one, I think, is the second set there, where the agent was programmed with MA DDPG, whereas the adversary was traditional DDPG. And you can see that in this case, the agent did much better, and that's sort of telling how much better the multi-agent version of the algorithm is than the single agent version, with scores in around 85% success. So it's a really telling graphic in that second set. Likewise, the third set, sort of the opposite case of that, where the agent was programmed with the traditional DDPG, and the adversary programmed using the multi-agent version. And here you can see that the adversary actually did much better because the agent had a relatively low score. So, and then you can see the last one just compared both DDPG algorithms for adversary and agent, and you can kind of see the troubles that excuse me, that algorithm just had in general. And so the takeaway here is the authors kind of showed that the multi-agent version of this algorithm really was a big improvement over the traditional DDPG. So with that, just a summary of today's webinar. We talked about how multi-agent environments are non-stationary, and the actions of other agents, they complicate the learning process, and high variance impedes the policy gradient kind of methods. So the authors of this paper we talked about today came with this multi-agent version. It's based on the DDPG algorithm, the actor critic standard algorithm. The main change that they made was to have the critic use a shared replay buffer that gives the critic access to the actions and experience of all the other agents that are in the environment. That's used in training, but then during execution or operation, the actors are used, and they only have access to local information, so they can act independently of one another. And then we talked about several environments. This was demonstrated with, and how the performance of the multi-agent version of DDPG significantly outperformed the traditional DDPG in those different test environments. So as I said, it's a very interesting algorithm. It's a pretty simple extension of the traditional DDPG. I think you'll find in the last programming project for the Deep Reinforcement Learning nano degree, it's a environment where you train 2 agents that are cooperating with one another to play table tennis. So it's kind of a cooperation. You could treat it as a competition, but in this particular one, the metric is how long you can keep the ball in play. So they actually are cooperating with one another to keep the ping pong ball in play, and you basically train them to be able to move the ping pong paddle to hit the ball and knock it across the net, and not have it go off the table, and have volleys go back and forth. It's a pretty complicated environment. You probably find it might take a couple thousand episodes to train these environments. But if you use a multi-agent DDPG, I think you'll find you have a better chance of success. So with that, good luck on that project, and hope that you use MADDPG in the future. It's a good algorithm to use. With that, I'll say good night.